started. By the end of this week, you should be able to do the entire homework. It's going to take some time. It may not be the easiest homework you've ever done, so please put some effort into it. Unless, of course, you've already seen this kind of stuff. In this case, this is actually a very easy homework. How many people have started? There's some discussion, very little, and you know, not too many people are raising their hands. That's a bit worrisome. I feel like I have to tell you. I will end up telling you on next Tuesday. I told you so. So please start soon. You should have received feedback on your projects. And some of you have written back to me, and I'm kind of processing responses. Some of you want to meet with me. I encourage you to come to my office hours because seems like scheduling seems to be a bit of an issue right now. Otherwise, I'll try to find some time. If you can't make it to my office hours, let me know. I'll try to find some time. One way or another, please start working on your project. At least start thinking about it because this is probably the most important part of the class. This is where you will learn without, you will learn to apply what you see in this kind of an unconstrained fashion. There are no rules, or there are very little structure around it. So I think that because many of you are working on something that you care about, you'll end up actually putting some effort into it. As I mentioned earlier, my interest in your project is because so many of you are doing such cool stuff. I hope to learn something. And those of you who are doing the competitive project, I can't tell you how excited I am. Every morning I wake up and I go to Kaggle and see the TV curve moving or not. Right now the current high score is 82%. I see only like 11 of you are actively competing, and I know more than 11 of you have signed up for that, so please start doing that. There will be an intermediate report due, I think, I can't remember when, sometime soon, maybe 2 or 3 weeks. So
it says the 3rd.
November 3rd?
It says November 3rd, next Thursday.
So probably I might extend it by a little bit, maybe a week, but not too much. And for your intermediate report, all you have to tell me is, how's it going, basically. Those of you who are doing the competitive project, I expect that you would have at least tried out 2 algorithms by then. For the regular project, I expect that you got your hands on the data, you've got your train and test split, you have at least done some pre-processing. If you're I think almost everyone, or probably all but 1 or 2 of you are doing experimental projects. So the stumbling block is invariably data. So I expect that you have your data, you should have done some initial analysis. Your intermediate report should tell me how many examples there are, what's the size of the data, what's the dimensionality of your initial feature set that you might be thinking about. Or some of you are doing online learning, so you should tell me, basically describe where you are. The one way to not get a good grade in the intermediate report is if you say, oh, I didn't do anything. That's a guaranteed way of not doing too well. So please put some effort into that. Any questions about any of these things? So just to summarize, there's a homework, homework 4, and hopefully you guys have started your project. Alright, so there are no questions. I'm going to move ahead and continue where we left off. Just to recap where we were, in the last lecture I spoke about agnostic learning. Agnostic learning is a somewhat more realistic setting where we don't assume that the learning algorithm can ever find a function that perfectly fits the training set. So earlier we saw this Occam's razor thing where we said that the learning algorithm finds a classifier that is perfectly consistent with the entire training set, and we asked, can we say anything about the quality of the classifier it produces if it fits a large training set? And in the Occam's razor setting, what we saw was, yes, we can. We can say that if the hypothesis class is small enough and the learning algorithm finds a classifier inside this hypothesis class that perfectly fits the training set, then there's some hope of generalization. In particular, we saw the statement that we saw was the number of, if you have more than roughly log size of the hypothesis class number of examples, and one of these hypotheses fits the training set, then with high probability you have found a classifier that has low error. With probability 1 minus delta, you found a classifier that has an error less than epsilon. So this was the consistent learning algorithm setting, and immediately I pointed out right after we finished that this is kind of unreasonable because there's no hope that we can ever find a consistent classifier in a realistic data set. Then we moved to another setting that is called agnostic learning, and in agnostic learning we threw away the consistency expectation. We basically said, remember this picture, there is a concept class C, and nature is free to pick any function inside this concept class that looks like Hartman and squat out. Nature can pick any point inside that, and the hypothesis class, the learning algorithm, is free to pick any hypothesis class which may not contain this concept class. So you could have this kind of hypothesis class. So if nature picks a function here, there's no way you can find that function because it doesn't. It's not even in the search set. It's not even in the hypothesis class. And in fact, a variant of this that I forgot to mention is something more extreme. Let's say this is the concept class and this is the hypothesis class. There's no overlap. You can't. We have no way of knowing where the concept class is. So we're going to search where we find where we can do something reasonable. And in this case, I mentioned that we have no hope of finding getting zero training error anymore, which means all we can hope for is to find a classifier that has a low training error. And then the question is, if I pick a classifier that has, say, a low training error, or even let's say the minimum training error, the hypothesis that has the minimum training error among all the functions in the hypothesis class, let's say we find that. How much worse will that hypothesis be in the future? That's the game we are trying to play. That's the question we are trying to ask. And in the last lecture, I stepped through this proof by working through the law of not the law of large numbers, by bounding the tail probabilities. Remember Chernoff-Heffding inequalities. And in your homework, you're going to be playing with more Chernoff-Heffding inequalities, so you might have to kind of go through that again. Anyway, it turns out that using the Heffding inequality, you can get a similar sort of a guarantee as what we had in the previous case. If you have m training examples, and m is more than these many, now this quantity on the right side, and you should be able to prove how to get the quantity on the right side. If you have these many training examples, then the difference, then you can make an epsilon delta guarantee of the following form. With probability more than 1 minus delta, your learning algorithm has found a classifier whose error is only epsilon, is no more than epsilon greater than the training error. Remember, we are no longer saying the error is more than epsilon. All we are saying is the error is epsilon more than the training error. So notice that this has a very similar form. Once again, we have a log dependency on the size of the hypothesis class, which is pretty cool. I mean, we are in the setting where we have no idea whether the hypothesis class and the concept class overlap, and yet we are able to make this kind of an Occam's razor sort of a statement. I can rewrite this as a generalization bound, and I see this is also called point 1, so both are equally important. We can rewrite this as a generalization bound. What that means is, we can say, we can put a bound on how much worse can the generalization error be. The true error or the generalization error, if I just put the difference between the true error and the training error has to be less than this quantity, which is very cool. If the training error is low, that means the expected error, the generalization error will also be low. So what we are saying here is, I don't care what your future examples will be. If your future examples come from the same distribution as the training data, and you pick a classifier that has a training error of this much, then your true error will be no more than the training error plus the thing in the circle. And the thing in the circle is again a function of, let's examine this a little. If your hypothesis space is large, then the bound becomes weaker. This thing in the circle becomes larger. So the generalization bound becomes weaker. So the intuition is pick small hypothesis spaces. If you demand that the guarantee be very high, namely delta is small, then your error, the guarantee on your error itself might actually become larger. If you have very few training examples, if m is small, then your generalization error is weak. So if you wanted to know why we need a lot of training examples, here's the answer. If you have more training examples, then you get better generalization. Because if m is large, the whole quantity inside the circle becomes small. So you get a tighter bound on the difference between the training and test error. And if you find the classifier that has the minimum training error, you're getting close to probably the minimum generalization error. This kind of a statement is called a generalization bound. Questions? So everyone understands everything perfectly. Alright, so if there are no questions, I'm going to move ahead. So let's just recap what we saw so far. What I called Occam's razor, actually this name is a bit weak. Under the section of Occam's razor, I presented this case where if the hypothesis class contains the true concept, then you should be able to find a function that fits any training set, right? Like the decision tree sort of thing. In that case, we had this bound. We said that if you have these many examples, then you can get the epsilon delta guarantee. The agnostic setting, if the hypothesis class does not contain or may not contain the true concept, then we got another bound, which looks incredibly similar except for this extra thing that you have to pay. Smaller errors cost more in the agnostic setting. Demanding a smaller error costs more in the agnostic setting. Right? So, the lesson, if you want to generalize this into one higher level concept, the ability to learn depends on the size of the hypothesis class, whether or not you care about the hypothesis class containing the true concept. Bigger hypothesis classes, it means it's going to be harder to learn. When I say harder to learn, it means the sample complexity is more. The number of examples needed to make a strong statement about your classifier is more. Right? So, the ability to learn depends on the size of the hypothesis class. So, have you solved everything? Have you understood everything worth learning? What can we say about linear classifiers using this?
Well, the size of the linear classifier hypothesis class is infinite, so...
Exactly. How many lines are there on the plane? Or how many hyperplanes are there in a d-dimensional space? An infinite number. So, if you apply this theory naively, it seems as if you need an infinite number of training examples to find linear classifiers. Of course that's not true. We proved that's not true because we proved the perceptron mistake bound. I mean, that's kind of not the exact sort of statement, but this theory does not analyze infinite hypothesis classes. So the one thing that changed from the top to bottom is consistency. Agnostic learning no longer requires consistency, but in both cases, we still had two assumptions. Can someone tell me what the two assumptions were? What's the basic assumption that we have for batch learning? IID and fixed and unknown distribution from a fixed unknown distribution. Examples, both training examples and future examples are drawn from the same distribution. That's not changed here. And we made one extra assumption. We assumed that the size of the hypothesis class is finite. There is a finite number of functions, like Boolean functions, for example, and the learning algorithm. We never said anything about a particular learning algorithm, really. Whatever learning algorithm there might be, it picks one of them. We will drop the second assumption now. Namely, we'll still carry on with the same game that we had before. Examples are chosen IID from a fixed distribution. But what if the hypothesis is not finite? The hypothesis class is not finite. Do you agree that this theory does not capture that setting? Okay, let's now explore that. But before we go ahead, are there any questions about any of this stuff? Because we're going to do a bit of a slightly different thing right now after this. Yes?
So, though the agnostic learning is guaranteeing the confidence accuracy on the training set, not the actual generalization.
Sorry?
So can you go back one more slide? I think I failed to ask the question.
This is bad.
Oh, never mind.
No, I'll be there, don't worry. It's only like 83 or something.
Yeah, great.
Could probably split this into multiple presentations. That might. Yeah.
Right, so we are talking about the error on the train, so the confidence on the training error, and then we apply the generalization bound to throw it into the generalization error, is that correct?
Not quite. So, first of all, I want you to convince yourself, maybe not now but later, that these two things are actually the same thing. Because epsilon here, let me be more careful, this epsilon is actually this thing. Epsilon is the difference between the generalization error and the training error. And all I have done is move the epsilon to the left side and then move the m down, take a square root, and that's it. Okay? And the definition of epsilon is how much worse can the generalization error be than the training error? How much more can the how much more is the generalization error than the training error? So, in some sense, what we are asking here is so first of all, before say interpreting this, these two are identical statements, just written in two different ways. The first interpretation is how many examples do you need? The second interpretation, which is probably related to your question, is suppose my training error is 0.1, let's say. Let's kind of let's put numbers here. Let's say the training error is 0.1. Then what this statement says is the generalization error of that particular hypothesis has to be less than 0.1 plus this quantity. If that quantity is small, let's say that the size of the hypothesis class is extremely tiny. Let's say, and delta is some number that we may or may not have to worry about right now. And you have 100 examples. Let's make this concrete. Let's say log size of hypothesis class is some number, let's say the dimensionality n. Then this is simply n plus log 1 over delta divided by 2m. So if you have 100 dimensional examples and you have 100 examples, Okay. If you have a small number of examples, then you cannot say much. Really what this statement is asking is, in some sense, if you think about the meaning of the delta, let's think about the meaning of the delta. The probability that this statement is true is more than 1 minus delta. With high probability, your generalization error will be less than 0.1 plus the square root of 10. And if the thing inside the square root here is small, then you can say that your generalization error is not too bad. It won't be too much worse. And in some sense, this is the motivation for finding a classifier that has low training error. Because if you have low training error, these things might be fixed. You have as many training examples as you have. The dimensionality is whatever it is. So the only thing that you can control is this confidence thing, but that's basically that shows up on both sides here. So n and m are fixed. So now among the multiple hypotheses that are there, which one do you pick? And this theorem says, this statement says, pick the one that has the low training error. Because if you have low training error, you will have low generalization error. That's the way to interpret this. Yes?
How does this bound change if I'm not able to keep up the IID assumption?
Oh, everything, in fact, that you have to rederive everything from scratch. IID is what let us, IID is what let us, let's see if this works. Okay. The IID assumption is the thing that, let's just go from the first expression to the second one here. And you can't do that without IID. So things change, you have to rederive things from scratch. And
there is some bound.
There is some bound, and maybe I'll put it in an example. Alright. So, other questions?
Was that a joke?
Probably. I don't know.
High confidence.
With some confidence, yes. Yes.
So if we are considering the lowest training error, so are you not overfitting?
Yes, that's the thing. On one hand, we see that's. I was hoping somebody would ask me that, because on one hand, it seems that we might end up overfitting. And yet, the theory tells us that you will not overfit if you appropriately control this side of the thing. In fact, this is the way we end up getting support vector machines. Support vector machine says minimize not just the training error, but the training error plus some other quantity. So this one, the statement that I made earlier was, if you pick the classifier that has a low training error, then your generalization error will be less than this side, this thing. Then it seems like the right thing to do would be to pick the thing that has the lowest training error, right? Turns out, not quite. A better thing to do is to pick a classifier that has low training error plus some other quantity that pushes for generalization error. And this, the second quantity is called the regularizer. We'll see the regularizer when we come to support vector machines. So, picking the classifier that has the lowest training error, yes, we will probably end up overfitting, which is why you need other things. Just not minimizing training error is not necessarily the best thing to do.
So,
I heard your voice, I saw your hand, so you guys can fight it out.
so are we saying that that there is a guarantee, but there really isn't?
No, the guarantee is always there. Notice that the guarantee is the sum of, the bound is the sum of two terms. Earlier, I said the second term is fixed. If the second term is fixed, the best thing to do is to find the low training error. Who said the second term is fixed? Maybe I can find a way to also minimize the second term and the first term together. Because minimizing the sum of these two terms is what we care about, not one or the other. If you fix the second term, then you have to minimize the training error. Minimizing the training error is the best thing to do. But we actually, in practice, do have the liberty to control the second term as well once we get to this infinite hypothesis space setting. I saw your hand before. Yes.
Maybe you can take it offline, but I'm struggling with the math here. Like on the first one, you have m is greater than equal to, and in the second equation, the signs are reversed. It's less than equal to.
You're right. That's a good observation, and let me think. So that is right actually. So there's a mistake. Let's see.
If you just move them around, then that.
No. Yeah. I see your point. If you literally just do what I said, the inequality changes. I think that's weird. I'll come back to this because I know that these things are correct. I have to think, and I'm not able to think on my feet right now. But yeah, good point. And if you don't mind, bring this up again in the next class. I have to think about this offline. Yes.
Okay, second, if we have to minimize both zero like error on a training set and the whole thing under the square, then like when you have many examples, then it's hard to overfit, right?
Right. Sure. That's right. If you have enough examples, overfitting may not be a bad thing to do. Even, right?
Yeah.
If you have enough training examples, maybe it's not a bad idea to overfit even. Overfitting is hard to do, but if you are able to overfit, then how could it possibly be bad with high probability? Yes. That's a good point actually. I have to think about this. So let me just come back. Yeah.
What's the definition of epsilon? Is error true minus error training or other?
Yeah, I think that's
I think that's a way.
I think that's the thing. The epsilon is greater than error D minus error S. And I think that's what will
The training error minus
The only way we can.
I think that I think that's how it will show up. Yeah. But I want to kind of work it out and let's come back to that. Alright, so good questions. I feel like at this point you're ready to jump into this a completely different thing, which is this idea of quantifying sizes of infinite hypothesis spaces without just saying the size of the hypothesis space is infinite. And to get there, we need to go through this idea of shattering and VC dimension. So everything that we saw so far was restricted to finite hypothesis classes. But it's not terribly hard to see that some infinite hypothesis classes are more expressive than some other infinite hypothesis classes. So, a line only divides the space into two parts. So does a funny little curve. But one might argue that the set of funny little curves is more expressive than the set of lines. In a vague kind of a way. So another, what's the example I have? Yeah, rectangles can capture fewer functions than what's the number? 17-sided polygons. Because in some sense there are more 17-sided polygons than rectangles. But how do we quantify this? We need a measure that tells what the size of the infinite hypothesis class. And it turns out the right measure, and we'll not get into the details of why, but the right measure is something called the Vapnik-Chervonenkis dimension, VC dimension. These two guys are like legends in machine learning. Vapnik is now 94 or something, and he's at Facebook. That doesn't mean he has a Facebook account. He works at Facebook. Chervonenkis, we passed away earlier this decade, but they did some of the most foundational work in machine learning. The VC dimension does not have a lineage in machine learning. It basically comes from geometry, and it's simply asking what is the and for our purposes, you can think of it as what's the expressive capacity of a set of functions. It is like a size of a hypothesis class. In fact, it's like the log size of the hypothesis class, and once we compute the VC dimension, we will get to the point where we can almost basically plug in the VC dimension instead of log size of h in the bounds that we had. So VC dimension is a way of computing the size of hypothesis classes for infinite sets, infinite hypothesis classes. So I want to kind of introduce this idea using examples, because invariably I have found that this is a somewhat tricky concept to grasp. Let's consider the problem of learning rectangles. So this is called an axis parallel rectangle for obvious reasons. And the classifier is defined in the following way. If a point comes from inside the rectangle, it's positive. If a point comes from outside the rectangle, it's negative. And let's even make our lives easier. Let's say that one of the points of this rectangle is the origin. So we are essentially growing, never mind. Let's just consider axis parallel rectangles, because that's equally simple. Alright. Now, let's say we get some training set. And the rectangle that you're seeing right now is the true classifier. We want to find that rectangle using training set. So that's the true classifier. We get 3 training examples, and I can draw a rectangle around the positives, and I get 0 training error, right? Every point inside the rectangle is classified correctly. Every point inside the rectangle is classified as positive. We have 2 positive points, and we just put a rectangle around those 2 points. So that's a valid function. I get a few more positive points, I can grow the rectangle. I can get a few more positive points, I may grow or not. I can always find a rectangle, not always, but for any of these, any consistent set of points, I can find a rectangle that agrees with that. Now, my question to you, let's say you get one more, I can find one more. My question to you is, will we be able to learn the target rectangle exactly? What do you think? Let's try, yes.
No, because I guess whatever rectangle you pick, you can just, is basically you have an infinite number of rectangles, you can only make the rectangle bigger.
Yes.
So,
So if you tell me that I've come very, very close to the rectangle and that's good enough, and that there is infinite space between any 2 rectangles. So if I come really close enough, I can zoom in, and there's infinite space. I can always find more points that are outside, positive examples that are inside the true rectangle but outside the one that you picked. Right? Okay? Now, but we can come arbitrarily close to the true one. Moreover, if I only have a finite set of examples, this rectangle that I just drew is just as good as this other one, assuming that's a rectangle, right? Make sense? So, we have some leeway. I mean, it's not just one rectangle that we are trying to find, there's a whole bunch of rectangles that are equally good. So is this one. There's a whole bunch of rectangles that have the same training error, they are equivalent. So that's the first thing to note. It's not the number of functions that we care about, it's the number of ways in which we can partition the positives and the negatives using this function, using the set of rectangles. And the rectangles that I drew here, this one, 1, 2, and all the ones that were there on the slide before, or let's call this one 3. 1, 2, and 3 are equivalent in some sense. They belong to the same equivalence class because they partition the training set in the same way. So let's think about how expressive functions can be. I have 2 points here, and I can split these 2 points in 4 ways using a line. So if I call this plus and this minus, I can separate the pluses and the minuses. If I call with the line pointing in this direction. If I call both of these pluses, then the line points in this direction. If I call this plus and this minus, the line points in this direction, and both of them are minus, I can put a line. So if I have 2 points, it doesn't matter how you label those 2 points, I can always find a line. I just demonstrated that by enumerating all possible cases. What if you have, so before coming to the hypothetical, the way we say this is lines in 2 dimensions can shatter 2 points. Lines in 2 dimensions can label can agree, you can always find a line in 2 dimensions that agrees with any possible labeling of 2 points. This means lines can shatter 2 points. Can lines shatter 14 points? I spent some time a few years back putting 14 points, and sure, what about these 14, this labeling? I can find a line, but does this mean it can shatter any labeling? Here's another labeling. There's no line that agrees with this coloring of the points. It means that there exists a certain coloring of the points such that there is no line that can label, that can agree with this labeling. Another way of saying this is lines in 2 dimensions or linear classifiers in 2 dimensions cannot shatter 14 points because there is a labeling that cannot be separated by lines. Okay, so that's the intuition behind the idea called shattering. On the other hand, there are certain functions that can shatter 14 points. I could potentially, any way in which you label these 14 points, I can find a squiggly curve that perfectly separates the positives and the negatives. It's not that you cannot shatter 14 points, it's just that you cannot do it with lines. There are squiggles that do. High degree polynomial classifiers can shatter 14 points. It just so happens that lines cannot. Is the intuition, does it make sense? So this is the argument that I'll be trying to push, which is there are some functions, even in 2 dimensions, that are more expressive than others. Squiggly curves are more expressive than lines. Lines can only shatter 2 points. Lines can shatter 3 points, but not more. Let's formally define shattering. Say you have a set of examples, a finite set of examples, like those 14 points. That finite set is shattered by a hypothesis class H if it doesn't matter how you label those finite set of points, I can find a function that agrees with that label. I'll walk you through examples of these things, but let me repeat the definition. You have a finite set of points, and in some sense, every way in which someone labels those points, you can find a representative in your hypothesis class that agrees with that labeling, that classifies the points exactly the same way as the labeling did. Then you say the hypothesis class shatters the set of points. The shattering dimension of the hypothesis class is the size of the set of points, at least the size of the set of points. And the intuition is that a richer set of functions can shatter more points. Like squiggly lines can shatter 14 points or more. Lines cannot. So let me work through an example. Let's say this hypothesis class we consider is a set of what's called left bounded intervals. It's simply this function where the instance space is just positive numbers. So you just have a number line, and this is 0, so all positive numbers. You get a point here, and the hypothesis is defined by a number A, and any point inside this interval is labeled as positive, every point outside is labeled as negative. That's the hypothesis class. The hypothesis class is completely defined by this number A. If I change A and move it here, the set of positives is this one. Now, in some sense, if I frame this as a learning problem, the goal of learning is to find this threshold. I need to find, given a set of points, I need to find an A such that it agrees with the training set. Now, let's try to work through the definition of shattering to see how many points this hypothesis class can shatter. So, let's go one at a time. Say the size of S equals 1. Basically, your training set consists of 1 point. The definition of shattering is, let's say this is that point, it's on the number line. This is the point, this is 0. This is the point that's in S. Now, if this point, now to actually see if the hypothesis class can shatter this 1 point, the way you go ahead is, you try out every possible labeling of the entire set of points. Here we have only 1 point, so we can go methodically. Let's say this point was labeled plus. Can you find a function that correctly, in the hypothesis class, that correctly classifies this point?
Label everything positive?
Label everything positive, or can you find me a particular value of A? Let's say this point is the point 1. A is 2. If A is 2, everything inside is labeled as positive, so you have found a classifier, both of you in fact, found a classifier that in the hypothesis space that agrees with this labeling. Okay, but we are not done. Maybe you will not be able to find a classifier when this point is labeled minus. Can you? A has to be, A is 0. No, A has to be more than 0. A is 0.5. So you're putting the bracket inside. So you're saying that everything here is positive, everything outside is negative. So what you have done is, I gave you a point, and in every way that I labeled the point, you were able to come up with a function that correctly labeled the point the way I did. This means this particular hypothesis class, which is called the left bounded interval, shatters sets of 1 point. Okay, maybe I'll be able to fool you with 2 points. So let's go back. So let's say the size of the hypothesis space is 2. Let's consider the general case. This is 0, I have 1 point here and 1 point here. Let's work through the same argument again. Let's just say that without loss of generality, I'm going to say that this is point 1 and 2. Now, the first, again, we have to start from the beginning. I have to consider every possible labeling of these 2 points. So let's consider both of them are labeled plus. Can you find me an A? 2.5. 2.5. So if I put A here, everything here is positive, so life is good. Okay. What about both minuses? Something here. Okay. What about this one being plus? In between. Okay, you know where I'm going, right? So this is minus and this is plus. You can't do it. If I put the classifier here, that means I'm making a mistake on 1. If I put the classifier here, I'm making a mistake on 1 and 2. If I put the classifier here, I'm making a mistake on 2. So this means there exists a labeling of 2 points for which you cannot find a function that correctly classifies, that agrees with that labeling. Just one labeling, but that's enough. This means left bounded intervals cannot shatter 2 points. Left bounded intervals can shatter 1 point because every way in which I labeled that point, there were only 2 ways. Every way in which I labeled that point, you were able to discover a function that agrees with that label. It cannot shatter 2 points because there exists one way of labeling those points where there is no function in the hypothesis space that agrees with that label. Make sense? Yes?
And does the points in the training set, do those have to be greater than 0 as well?
Yeah, sure.
Well, I was going to say, because
No.
with 1 point, if you put it at 0,
Yeah, but you're talking technicalities here. Yeah, this is an example, so I have some liberty. Okay, so the lesson here is 2 points cannot be shattered. Then given two, and the way this almost is a recipe. Given a set of 2 points, you can label them in a way such that there is no function inside the set of functions that we are considering that agrees with that label. So 2 points cannot be shattered by this function class. Notice that this function class is infinite because the set of A's can be arbitrarily large, but we don't care. In this thing, if this function is, for all practical purposes, for this training set, the same as this function. That's how we are getting around the infinite set of infinite functions, because we are bucketing them into equivalence classes. Alright, let's consider another set of functions. This time, something like what you would ask for. The inputs are all real numbers, and now, let's say this is 0. The input can be all real numbers, and the function is defined not just by bounding on the left, but you're putting bounding on both sides, and it doesn't have to be both on different sides of the origin. So you have 2 numbers, b and a, and everything inside is labeled as positive. Okay, is the function class clear? This is just intervals on the real axis. Alright, so again, let's walk through the same process. Can sets of 1 be shattered? If the size of S equals 1, I have 1 point, doesn't matter where it is because the origin is no longer important. And the function is defined by 2 numbers, a and b, and every point in between a and b is labeled as positive. So can you give me, let's say that to check if this set can be shattered by this function class, I need to consider every possible label. So here's the labeling. Can you tell me a function? You need to give me 2 numbers, a and b. Once again, can't.
Oh, sorry, just on either side.
Okay, on either side. So something like this. Everything inside between the brackets is labeled as positive, so you found a function. Okay, what if it's negative?
So the right.
Basically you put the bracket outside. And everything in between here is labeled as positive, and everything outside is labeled as negative. So here's a function that agrees with this labeling. So for every labeling of 1 point, you can find a classifier that agrees with the labeling. Another way of saying that is for every dichotomy of the data, there exists a function that can predict that dichotomy. Okay, so let's move ahead. 2 points. Remember earlier 2 points did not work out. So you have, in the previous case, 2 points were not, you could not label 2 points. Can we do that now? Let's consider all possible cases. I'm just going to write them all down. Plus plus, minus minus. For plus plus, of course I can put the brackets on both sides of the plus and I'm done. What about the second one? Anything outside, so this time I'll put it here. What about plus minus? Just put a bracket around the plus. And for the last one? Oh, yeah, something like this. So, here's an example of a more expressive function class than what we saw before. Left-bounded intervals could not shatter this, but general intervals can shatter 2 points. Okay? Yes?
Is there any form of like inverse with this? Because like with the left-bounded interval, you can't shatter 2 points, but if you just invert what's plus and minus, it can.
Yeah, but then you can't shatter, even there you can't shatter 2 points, because I can find another example. Right-bounded, you're talking about right-bounded intervals. So, if this side,
Yeah.
then I'll give you 2 points and label this as positive and this as negative.
Okay. So it doesn't matter that it can separate them correctly, they have to be labeled correctly.
Yes, it has to agree with the label. Alright, so for s equals 3 it works. Let's try one more. S equals 2 it works, s equals 3. So I have 3 points, and then let me just get rid of Now it's going to be a little bit of a pain, so I'm not going to list all of them. So I have 3 points. Can you find, I'm going to argue that 3 points cannot be shattered. And the way you prove it to me is you need to find a labeling of these 3 points.
Yeah.
Plus, minus, plus. Excellent, you're catching on. So plus, minus, plus cannot, there is no function inside the hypothesis class that can produce a plus, minus, plus. So 3 points cannot be shattered. The way you prove that a function, a set of points cannot be shattered is all you need to do is find one labeling that does not agree, such that there is no function that can agree. So 3 points cannot be shattered by intervals, whereas 2 points can. One more. Alright, so this is just what I said just now. One more example. Let's go to the function class that you guys must be really familiar with, linear classifiers, which are also called half spaces in a plane. Half spaces because the line splits the space into 2 halves. Now, let's consider 2 dimensions because that's all I can draw right now. Can 1 point be shattered with a line? So, let's use this space here. I have 1 point. So, I have a point, okay, and I label it as plus. Can you find a line that correctly agrees with this point? I see that you drew the line in the air, I will just mimic your action. This is a plus. Okay? If this was a minus, I will just be lazy and point the arrow the other way. So, lines or half spaces in 2 dimensions can shatter 1 point. Okay, let's go to 2. Can you shatter 2 points? I have. So plus plus. Something like this. Okay, what about and minus minus, of course you can. What about plus minus? Just draw it in between. And minus plus is just the opposite of that. So draw it in between, point the line in this direction. And minus plus is just change the, just negate the weights. So 2 points can be shattered. What about 3? Let's try. Sorry? Aha! So this is our first hitch. So let's first consider collinear. Can this be shattered? No, clearly not, because I'll put the minus in the middle and plus on both sides. So it seems like there exists a set of 3 points that cannot be shattered. But for shattering, we have to, shattering is defined for a set of points, and these 3 points are not shatterable. But there are also 3 points that can be shattered. Right? So if I label them all as plus, then I just put the line anywhere and point it this way. If I label them all minus, I just point the line the other way. If I have 1 minus and 2 pluses, I draw the line in between, and that's all there is. 1 minus and 2 pluses. If I have 1 plus and 2 minuses, I just change the direction of the line. So, this is interesting. There are sets of 3 points that can be shattered, and there are sets of 3 points that cannot be shattered by a line. But remember, shattering, the definition of shattering is for a set of examples. A set of examples, one particular set of examples, or many sets of examples cannot be shattered by lines. And there are sets of examples that are not collinear, that can be shattered by half spaces. On the other hand, turns out 4 points cannot be shattered. No set of 4 points can be shattered. Let's prove that. Okay. First of all, let's say I have 4 points, and let's say 3 of them lie on a line. The 4th one does or does not, I don't care. If 3 of them lie on a line, can you find me a labeling that cannot be shattered? Let's call this points 1, 2, 3 and 4. Plus, minus, plus, and 4 it doesn't really matter, because even this you cannot find a line. Okay? So, if I have to prove this formally, I have to consider the other case. I'm trying to prove that no set of 4 points can be shattered. There are only two kinds of sets of 4 points. Sets where 3 points are collinear and sets where 3 points are not collinear. I mean, this is just an arbitrary thing, but it seems to work for this proof. So let's consider the case when 3 points are not collinear. The way to prove it is, if 3 points are not collinear, there must be, points can exist only in one of two ways. Either the fourth point lies inside the convex hull. The convex hull is just the triangle that connects 3 points. If it exists, if the fourth point lies inside, I'll just label the points outside as plus and the point inside as minus. Right? The point lies outside the convex hull. What do? Can you find a labeling of this that cannot be shattered?
Checkerboard.
The checkerboard. What I like to call as the XOR function, because you have pluses and minuses. So just by analyzing all possible cases, there are 3 cases. Case 1, 3 points are out of the 4 points, some 3 points are collinear, cannot be shattered. Case 2, out of the 4 points, 3 points form a triangle and the fourth one lies inside the triangle, cannot be shattered, because you were able to find a labeling that cannot be linearly separated. Case 3, no 3 of, like out of the 4 points, no 3 of them are collinear, and the fourth one does not lie inside the triangle formed by the first 3. Then you take this kind of an XOR labeling. In every arrangement of 4 points, every way I tried to arrange the 4 points, you were able to produce a labeling for which I cannot classify that label, the point. This means the set of 4 points, no set of 4 points can be shattered, because I have basically exhausted all possible arrangements of 4 points. I was able to find one arrangement of 3 points that was shatterable, that's the triangle, but no arrangement of 4 points can be shattered. At this point, I feel like I should pause for questions. Yes?
So a line can only shatter 2 then?
3.
But we just came up with an example that you couldn't shatter.
Yeah, but there are sets of 3 points that can be shattered.
But you said that if we could come up with one example you could not shatter, then it's done.
Aha! This is where people get confused. If you are able to, I give you a set of points. You try to label it. If you are able to find one labeling of the set of points that cannot be classified, then the set is not shatterable. Shattering is a property of 2 things. It's a property of a set of points and a hypothesis space. So, it's an adversarial game between you and an adversary. You claim that a hypothesis space can shatter a set of D points. A particular set. You find the set of D points. The adversary says that's not possible. And here's a labeling that you cannot classify. The adversary label. And you find, if you're able to find a function that predicts the labeling, then the adversary loses. So the set of points is fixed. The adversary can pick the worst possible labeling. In some sense, the adversary picks a labeling that tries to defeat your hypothesis space. Yes?
Would the VC dimension for a line then be 3 or 2?
3. I haven't defined the VC dimension, but yes, it's 3. That might even be the next slide.
Wait,
No.
so who picks the points? Me or the adversary?
You pick the points. You pick the points so that you are in your most favorable setting.
Okay, so I do most favorable.
For the set of points, for the location of the points, the adversary picks the most unfavorable labeling.
So I would never want to pick 3 collinear points.
Exactly. Exactly. Or actually no, that's for VC dimension. We haven't gotten there yet. You pick the points. Pick the points that you want. You can pick collinear, it won't get shattered. But 3 collinear points will not get shattered. 3 non-collinear points will get shattered. It's just a property. But yes, if you want to prove that any set of 3, if you want there exists a set of 3 points that can be shattered, then you will pick the one that's most favorable for you. We will be trying to make statements of the following kind. There exists a set of D points that can be shattered, and for D plus 1 points, doesn't matter, there does not exist any set that can be shattered. So for the first statement, let's just worry about the first statement right now. I want to prove there exist 3 points that can be shattered by a line. I want to convince you that there exist 3 points that can be shattered by a line. It would be foolish of me to pick collinear points, because I am trying to convince you that there are 3 points that can be shattered, so I will pick this triangle. Right? Questions? More questions? Someone from this side. Nobody, you guys haven't spoken about that. Yes?
I'm a little confused. So you say that you can shatter 3 points in a line, but so that's based on like a restriction you're giving to like how the points can be arranged?
No, I was very careful with what I said. I said there exists a set of 3 points that can be shattered by a line.
So could you, is that different from something like the set of points where like positive examples, like their x value is always less than negative examples? Can you not make a restriction like that to show that that's like a set of points?
No. The idea of positives and negatives is not extra information on the location of the point.
Okay,
That's
so
the labeling.
You can't base the restriction of the sets on labeling.
On labeling. You have to, I just pick the set of points and the adversary picks the labeling.
Okay.
So in some sense, every possible label.
Okay.
Right. So if you are an adversary, you have to pick a labeling such that that particular set of points cannot be classified. So I do not get to control the labeling. If I want to convince you that there exists a set of points that can be shattered, I only pick the points, and you, if you were the adversary, would try out every possible labeling in an attempt to convince me that I am wrong.
Okay.
That's why it's an adversarial argument. In fact, yeah, that's right. Okay. Other questions? Yes.
So there's this an extension from this question where, say for left-bounded intervals, you were restricted to saying that from the bound to the thing it's positive and
Right,
negative.
sure.
Say for example, for a set of points and we have a line, the adversary says that everything above the line is always positive and everything.
Oh, the adversary, yeah, sure. Okay, but then you're changing the.
Then you can find set labelings that is exactly opposite, right? Like even though you shatter that point, you're going to take pluses, minuses, and minuses.
No, but you get to pick only, the adversary does not get to move the points, and you do not get to change the label.
I'm sorry?
So you have to pick the points and then you step away from the board. The adversary then picks the label.
Okay.
So in the situation that you described, if I understood correctly, you move the points based on the labeling.
Yeah, so if that is the case, then for left-bounded intervals, they can do it with 2 points, right? So you pick 2 points, the adversary labels them, and then you pick bound and label them.
Let's try that again. I'll play me and you play the adversary.
Okay.
So this is a line, this is 0, I pick a point. Let's say this is 1. Oh, and 2 points, right? So let's say this is 2 and this is 1.
So I pick minus and plus.
You pick minus and plus.
Now you can then pick the interval between 1 and this thing and say 1 to 1.5 is.
I can't because it's a left bounded interval. Hypothesis class is the set 0, a. So one of the ends of this interval has to be 0.
So it is 0 to 1.5, but the labeling is towards it's what.
But that's a different hypothesis class. The hypothesis class is defined in the following way. If the classifiers are defined as, if the point x is contained in this thing, then label equals plus. Else, label equals minus. That's the definition of the classifier. Right? So, does that answer your question?
Yeah.
Okay.
So it seems like most hypothesis classes we've seen, if you took the hypothesis class and the inverse of the hypothesis class, like a new hypothesis
Sure.
class, it seems like that usually increases the VC dimension by 1. Would that be true?
That seems true at first thought, but I might have to think about it a little more carefully, but it seems, notice that for hyperplanes, for example, the set of hyperplanes is symmetric, so it will not. In this case, it does.
Okay. So this is a line, right? Like when you combine left-bounded interval and right-bounded interval?
Yeah, basically, it's a line in one. It's not a line. It's a circle in 2 dimensions. In 1 dimension, actually. It's defined as the ball in 1 dimension. This is a ball that is whose center is at the origin. If you had both intervals, then I guess that's also it's like a half space. Yeah. Yes.
The purpose of VC dimension is to.
We haven't defined VC dimension yet, so a lot of you are talking about VC dimension, but we haven't defined it.
It looks like you want to measure the complexity of the hypothesis class.
Yes.
In some sense, want to quantify it. Are there more simple, intuitive, less tricky ways of quantifying complexity?
This is simple, intuitive, and not tricky at all. What more do you want?
How is it compared to like order of the hypothesis?
There are ways of reducing the order into this thing, into this framework. We'll get to that. I know what you're talking about, and I do not want to answer your question because I haven't defined VC dimension yet. Alright, so let's kind of think about this shattering thing a little more carefully. It turns out some functions are infinitely expressive. They can shatter infinite points. Doesn't matter what labeling you give to an infinite number of points, you'll be able to find a function that can classify that. And one way of thinking about this from the learning point of view is if you find a hypothesis class that shatters only a small number of points, you're introducing some bias into the learning. You're saying, I do not need a more complex function. A simple one will do. This is the same kind of Occam's bias that we introduced before. Lines are more simple than squiggly curves because lines can shatter a fewer number of points. More expressive functions can shatter more set of points. So intuitively, you can think of the number of points that can be shattered by a function class, as a measure of the complexity of this function class. So larger set of points are shattered by richer functions. So now finally we can define the VC dimension. In the box here I just have the definition of shattering, just so that you have it here, because it can get a bit confusing. The VC dimension is, at first glance it's fairly simple. It's the size of the largest finite subset of the instance space that can be shattered by a hypothesis class. It's the size of the largest finite subset of the hypothesis space that can be shattered by a particular hypothesis class. So if you have a hypothesis class, let's take left-bounded intervals as an example. If there is a subset of the hypothesis class of the instance space, if there's a set of examples of size D that can be shattered, then I would say the VC dimension is more than D. On the other hand, if there is a set of examples of size D, if no subset of examples of size D can be shattered, then VC dimension is strictly less than D. Okay? So in the examples that we worked out so far, let's try to make this argument. There is for left-bounded intervals, there was a subset of size 1, that S2, that could be shattered. So the VC dimension of left-bounded intervals is 1.
Some of the size 2 could be shattered, right?
For left-bounded intervals, none of them.
No, if you had plus plus, that could be shattered.
No, plus is a labeling. Shattering requires every possible labeling. This is why it gets tricky. Just to confuse you, I'm going to say the whole thing. For the VC dimension is the size of the largest finite set of the subset of the instance space, such that for every labeling of those points, there exists a function that that matches the labeling.
So it's for so if there's any positioning of points,
Such that it can be shattered.
any labeling.
Yes. Yes. If there's any positioning of the point such that every labeling can be classified, then the VC dimension is at least the number of points. If for any positioning of the points, no labeling can be classified, then the VC dimension is less than the number of points. So what I have actually managed to prove in the class is the VC dimension of half intervals is 1, because 2 points could not be shattered. The VC dimension of intervals is 2, because 3 points could not be shattered. There is, all you need to do is produce 2 points that could be shattered. Half space is in the plane. I was able to produce one set of 3 points that can be shattered, and I proved that no set of 4 points can be shattered. So for proving VC dimension, you need the proof. VC dimension proofs typically have 2 sides. You need to prove a lower bound and an upper bound. VC dimension is at least this much. To do that, you need to produce one set. A proof by example is good. VC dimension cannot be more than this much, or has to be less than that number. For that, you need to prove every arrangement of the points will not work, like we did for the line and 4 points. Questions? Alright, so a few more VC dimensions. If you take linear threshold units in D dimensions, all the stuff that you guys have been learning so far, the VC dimension of linear threshold units in D dimensions is D plus 1. Sometime towards the end of the semester, we'll get to neural networks. VC dimensions of neural networks is often roughly the number of parameters. That's a very loose statement, but it's very roughly true. We haven't talked about nearest neighbors yet, but I just wanted to mention this. The VC dimension of one nearest neighbors is infinite, and once we get to once we see the nearest neighbors classifier, you should try to prove this. Once again, richer function classes shatter larger sets of points. So in this order, one nearest neighbors is arbitrarily rich. It can represent any possible set of functions. We haven't seen that yet, so some of you may have seen one nearest neighbors. If not, we'll get to that at some point. So let's go back to why we are talking about this, why we took this massive data. I care about making this Occam's razor kind of statement or statements about agnostic learning in the case of infinite hypothesis classes. In some sense, I want to bound sample complexity. For what we saw before was for when the hypothesis class is finite, sample complexity depended on the size of the hypothesis space. It was actually log of the size of the hypothesis space. It turns out the VC dimension behaves like the log of the size of the hypothesis space. We can write down similar sorts of theorems, and you would be relieved to know that I won't be proving them or asking you to prove them. I'll just state it. If you have, let's consider the first case. If I care about I have m examples, and I'm able to find a classifier in a hypothesis space that is consistent with all of them. And if m is greater than this number here, notice that you have all these funny constants. Let's not worry about how they got here. If m is greater than this number, then with probability at least 1 minus delta, the hypothesis has generalization error less than epsilon. And this is a path guarantee. Notice that in some sense, if you ignore all the epsilons and the deltas, I have this VC of h. Earlier we used to have a log size of h. So the VC dimension behaves like the log of the size of the hypothesis space. And this is again an Occam's razor because this says simpler function classes are better. Because simpler function classes need fewer training examples. The sample complexity is lower. And of course, this is not the full story. This is just the definition of pack. This is just pack learning. For efficient pack learning, for that function class, you need to find a learning algorithm that can find the classifier in a polynomial time. Polynomial in what? 1 over epsilon, 1 over delta, and the VC dimension. I can make a similar statement like agnostic learning involving the VC dimension. This time the bound is way more complex. If you have m training examples, then the classifier with a classifier that has a training error of this much will have a generalization error no more than the training error plus this quantity. Agnostic learning. Once again, this says if you pick hypothesis spaces that have lower VC dimensions, it's a good thing. Earlier, in the similar sort of statement, just earlier today, the similar sort of statement, we had log size of the hypothesis classes. Now we have this function involving the VC dimension. Alright, so as an exercise, in fact, I think this might even be in your homework, try to find the VC dimension of finite hypothesis classes. In fact, your homework asks you to compute VC dimensions for different functions and kind of tease apart the idea of a VC dimension. So, what you need to know, I think we've come to the end of pack learning, 2 minutes left, I'll be able to complete the whole section. What you need to know is what is pack learning. You need to be able to define pack learning. Remember, it's just a definition about the nature of generalization. We consider two cases, finite and infinite hypothesis classes. In both of them, for the finite hypothesis class, we derived a connection between the size of the hypothesis class and sample complexity. How many examples do you need to make the epsilon delta guarantees? And the bottom line is, if your search space is smaller, then you need fewer examples. If I say it that way, it seems like an obvious thing to say. But we can make the statement more formal. In the infinite hypothesis setting, the complexity parameter is this VC dimension. And VC dimension can be tricky. Even people who work with VC dimensions for years often end up with trouble when you get to this argument of proving VC dimensions. So you have to go back and you need to work out a few examples for the idea to sink in. And the general lesson here is higher VC dimension means higher sample complexity. We can make the same kinds of consistent and agnostic learning statements in both cases. So that's the theory of computational learning. We talk about the theory of generalization, pack learning, and this theory lets us prove positive and negative results and all that. But a question that I often get is, why? Why bother with so much math? Just give me an algorithm, give me data, I'll run run it on some data and work it out. And I think this is the most important thing most important part of machine learning. It tells you what is learnability. By elevating the idea of learnability to the same standard as time and space complexity, we are able to ask whether certain functions can be learned. Mistake bounds, actually, we saw mistake bound learning, right? Turns out mistake bound learning implies pack learning. If I'm able to find the classifier in the mistake bound model, you can find a classifier in the pack bound model. It raises interesting theoretical questions. We'll get to that in a bit. In fact, the theoretical questions are the next 2 lectures. It directly leads to algorithms. If I'm able to find a classifier, if I'm able to prove something that a certain hypothesis class is weakly learnable, meaning I can always find a classifier that's just slightly better than chance. Does this mean you can find a classifier that is awesome, that is much that's close to perfect? It's not an obvious question. It turns out the answer to that question is something that you may have heard of before. It's called boosting. The answer to this question leads to what we call ensemble methods. We saw that the true error is bounded by training error plus something with VC dimension. And many of you asked the question, should you just minimize the training error? The answer is no, you can minimize the training error plus something with the VC dimension, and that is what leads to support vector machines. And historically, that's what led to support vector machines. So computational learning theory directly resulted in a lot of the industrial strength algorithms that exist. And that's where we are going next. Alright, I'm 2 minutes over time. I'll stop, I'll let you go. I have office hours, so you can come and bother me afterwards.